Okay, for chapter 20, we're going to talk about electromagnetic induction and waves. And so we'll talk about Faraday's law again, and Lenz's law, and electric generators, and back EMF, transformers, power transmission, and electromagnetic waves. So the first thing we want to talk about is induced EMF, Faraday's law, and Lenz's law. Bless you. We observe that when a magnet is moved near a conducting loop, a current is induced. When the motion stops, then the current stops. And so in figure A here, there's no motion between the magnet and the loop. And so if you check right here, there's no current being induced. However, if I move a magnet that has a magnetic field perpendicular to the current, then what we'll have is a negative current here. And then if I move it away in the other direction, I'll have a positive current. One is stronger and another is weaker. So on the other hand, when the loop moves parallel to the magnetic field, there's no current induced whatsoever. So they have to, it has to be perpendicular will give you the maximum current. So we conclude that the current is induced only when a magnet field moves through the loop, and then the induced EMF is produced in a loop or a complete circuit whenever a number of magnetic field lines passing through the plane of the loop or circuit changes. So changing current in one loop can induce a current in a second loop. And so here in this scenario, we have a magnetic field that goes through two different loops, and then we have a power source here where the current flows through, and that could have an impact on the second loop here. Okay, here we have a decreasing current and field, and it changes from a positive reading to a negative reading. So in order to measure the change in a magnetic field through a loop, we define what we call magnetic flux. And so the Greek letter phi, however you wish to pronounce it, is right here. And that represents magnetic flux. And it's basically a measure of the magnetic field times the area. And then that's usually proportional to the angle of how the area, cross-sectional area, is intercepted by the magnetic field. So the SI unit for magnetic flux is the Weber, or WB. And so here we have a magnetic field B going through a loop. That loop has a cross-sectional area, and a current can flow through that. But what we're looking at here is a side view. So for our angle theta, which is the measure, we can have 180 degrees or 0 degrees. And then here, if it is parallel to the field, if the loop is parallel to the field, then we would have 90 degrees. And then if it's not perpendicular or parallel to the field, whatever the angle is from the direction of the magnetic field will give us some sort of answer. And so the overall equation is going to be the magnetic flux phi is equal to the strength of the magnetic field times the area, cross-sectional area of the loop, and times cosine of the angle theta. And theta is the angle from the magnetic field. So here's where it's counterintuitive. You have your loop, which really looks like it's perpendicular to the field, and that's true. But what we're looking at is the area. The area is facing in the same direction of the magnetic field. If it faces in an opposite direction, then it'd be 180 degrees. So then Faraday's law for the induced EMF would then be negative n times the number of loops times the change in phi, or magnetic flux, all over the change in time. And we can clean it up and make it look like this. So the minus sign indicates the direction of the induced EMF, which is given by Lenz's law. So Lenz's law is simple. It says an an induced EMF in a wire loop or coil has a direction such that the current it creates produces its own magnetic field that opposes the change in magnetic flux through the loop or the coil. So if the magnetic field is increasing, the induced current will produce a field in the opposite direction, tending to decrease the field. The direction of the induced current is given by the right-hand thumb rule because it's a cross product of vectors. So with the thumb of the right hand pointing in the direction of the induced field, the fingers curl in the direction of the induced current. So if we look at this picture here, our thumb is showing us the direction of the induced magnetic field, and then our fingers will curl around the direction of the induced current. And just to kind of jump ahead a little bit, you can induce a magnetic field by applying a current to a loop, and you can induce a current by applying a magnetic field to a loop. So the two are interchangeable. So Lenz's law is a consequence of the conservation of energy. Another way of viewing Lenz's law is that the induced current is such that the flux through the loop tends to remain constant. So here we have an example in figure A where we can give a bar magnet that is generating a magnetic field, and if we give it a velocity into the loop, it can induce a current. And also, if we induce a current, we can increase the strength of the magnetic field. However, if we change or oppose the direction in which we put the magnet through, it can decrease the current. So the magnetic field has an influence on the induced current, and you can have a current have an effect on the magnetic field. So one way of changing the flux through a loop is to change its orientation with respect to the field. If this is done via some mechanical means, electricity can be generated. And so one thing I want to talk about is one cycle. So if when in this example of a loop that turns through a magnetic field, we can generate electricity, but it's an alternating current, and so you'll have a positive voltage and a negative voltage, and we call that alternating current. And it's a sinusoidal function, and so when we refer to one cycle, that's kind of like a period, and that's just one entire cycle, okay, or wavelength, I suppose, is one way you could think of it. And so the induced EMF is then, the EMF is equal to the negative of the number of turns times delta phi over delta t, or the magnetic flux over time. And that's also equal to, because remember we can calculate the flux, negative n, the number of turns or loops, times the strength or magnitude of the magnetic field times the cross-sectional area, and then delta cosine of omega t. And remember that omega represents the angular frequency of that all over time. So such a generator is also called an alternator. So an EME or an EMF as a function of time can also be represented by the initial EMF times sine of omega t, where this is the angular velocity. And I kind of blurred it out, but this is the lowercase omega. It's just a Greek letter that represents the angular frequency. I think I said speed before, but it's angular frequency. So in common usage, we refer to the frequency rather than the angular frequency. So the frequency can be measured as cycles per time, but the angular frequency is kind of a measure of this rotational motion. And so as the loop spins, we can measure the angular frequency, like how long it takes to make one full cycle, or we can measure the frequency and the fact of how long it takes to complete one full cycle. So the relationship between the two is that omega is actually equal to 2 pi times the regular frequency. So then an electric motor has a loop rotating in a magnetic field and will also create an induced EMF. Then back EMF is given by E sub B minus the voltage, or I'm sorry, equal to the voltage minus IR. So here we have a driving power source that produces a current. That current goes through the coils that has a it's an electric motor, but there's a magnetic field in order to make the motor spin. And when it spins, it actually produces what we call a back EMF. The battery representation here in our diagram of the back EMF induced by these coils. So it limits the current in the motor and can help protect it. So it may be thought of as a negative, but it's actually a positive. So a transformer can be used to reduce current while keeping power constant. This is useful in transmission lines where losses depend on the current. So remember that the relationship between power is that P power is equal to the current I times the voltage, and so reducing the current while the power remains unchanged means increasing the voltage. And so a basic transformer works in this way. Basically, you have an alternating current source. Usually it's wrapped around an iron core, and you have a primary coil and a secondary coil. And so the transformer works by induction. The AC current in the primary coil induces a current into the secondary coil. The voltage ratio depends on the number of coils and the number of loops in each coil. So here we have a high number of coils in the primary coil and a low number of coils in the secondary coil. So this is a step-down transformer, low voltage, high current output, where in our first figure A here we have a primary coil with lower loops in the primary coil and high loops in the secondary coil, and that's a step-up transformer, which means we have high voltage, low current output and maintaining the power. So our power is consistent and constant, and we are using the induced current through these coils to change, and this is why it's called a transformer, because it transforms current into voltage or voltage into current depending on our application. So then the ratio of the voltage can be derived by looking at the induced EMF. So we have the voltage of the secondary coil is equal to the number of loops in the secondary coil over the number of loops in the primary coil times the voltage in the primary primary coil. So then the power is constant, which means that IV sub P, or I sub P V sub P should be equal to I sub S V sub S. So another way to look at that is that the current of the secondary coil is equal to the number of loops in the primary coil over the number of loops in the secondary coil times the current that's going through the primary coil. So in reality, there's always some power loss because no energy transfer is 100% efficient between especially the primary and secondary coils due to resistance and flux leakage and self-induction. So currents can be induced in the bulk of the material itself. These are called eddy currents. Eddy currents can function as powerful brakes for a solid conductor moving in a magnetic field. Braking can be reduced by shaping the conductor to make current loops difficult to form. And so basically you can induce a current through a solid, and so here we have an example of a magnetic field generated from the north to south pole, and the velocity of the object is coming through here, and the current is induced, and notice that there is a force that's being applied that opposes the velocity. Here's a different angle of that, and then lastly, this is how these objects are designed. So Maxwell showed that how the current and magnetic fields could be viewed as a single electromagnetic field. This is based on the relationship between magnets' influences on magnetic fields' influence on current, and current's influence on magnetic fields. And so he observed the following properties. A time-varying magnetic field produces a time-varying electric field. He also noticed that a time-varying electric field produces a time-varying magnetic field. So we have studied the first, but the second is new. We will not study that in full detail in this chapter, but we'll use its consequences. So it's that second one we'll think about, but we won't necessarily mathematically show the exact correlation just yet. And so an accelerating charge produces an electromagnetic wave. The electric and the magnetic fields are perpendicular to each other, and the direction of the propagation of the wave looks like this. So here is an example of like a broadcast antenna, and basically you have magnetic fields and then there's an electric field, and so as a transmitter or antenna broadcasts an electromagnetic wave, there is this alternating of the currents, for the most part, kind of, or the electric fields I should say, kind of go through these kind of circular paths. And the circular paths, if you follow it here, the electric field goes this way and it's always perpendicular to the magnetic field, and then it'll generate another field. And so depending on the wave, you'll notice a difference in the direction of the electric fields and also an alternating of the magnetic fields. A better model to look at is this, and this is an example of the propagation of the wave. So in pink are the electric fields, which are always perpendicular to the magnetic field, and so as those change or increase, there's also a change in the magnetic fields. And so from one beginning to the end, or from peak to peak, we call that measurement a wavelength. And so the propagation of the wave looks like this. And notice that the electric fields are always perpendicular to the magnetic fields. So all electromagnetic waves travel at the same speed in a vacuum. So in a vacuum, all electromagnetic waves, regardless of frequency or wavelength, travel at a speed of c, which is 3 times 10 to the 8th power meters per second. It's actually 2.99 something something something, but our textbook and for our homework we're going to round that to 3.00. So this is also known as the speed of light, because light is an electromagnetic wave. So this finite speed of electromagnetic waves leads to delays in transmitting signals over long distances, such as spacecrafts. So when we broadcast something to one of the rover modules on Mars, there's a significant amount of time, even though it's traveling very, very fast. So an electromagnetic wave transmits energy, and its electric and magnetic fields are capable of accelerating charged particles. It will exert a force on any surface it intercepts. This phenomenon is called as radiation pressure. It is negligible in everyday experience, but could be used to power solar sails for interplanetary travel. So electromagnetic waves can have a different frequency, and different frequencies have been given different labels. Now right here in the middle, there's a very small bandwidth of visible light. This is what human beings can see. And so this is 700 nanometers, and this is the wavelength here. 700, 600 nanometers is about yellow, 550 is about green, 500 is blue, and then purple or violet is about 400, and then after that we have ultraviolet. So we have infrared to the left, which is red that we can't see, and then ultraviolet, which is to the right, which is something that we can't see, but it's on the other end of the spectrum. Notice that when the wavelength is larger, the frequency is smaller, so they're inversely proportional. If we want to put some numbers to those, power waves and radio waves, AM and then FM radio waves, you can see here the approximate wavelength, and then here is the the frequency, which is inversely proportional. And some typical sources of these types of waves. So a power wave comes from electric current. Radio waves are from electric currents and antennas. TV is the same. Microwaves have special vacuum tubes that generate microwaves. Infrared radiation comes from warm, hot bodies, stars. Visible light comes from stars and lamps and light bulbs. And ultraviolet lights we can have from very hot bodies and stars. And we do have ultraviolet UV lights. We can see them because their span does kind of bleed through to the visible light spectrum. X-rays, those are high-speed electron collisions and atomic processes. And then gamma rays are usually released in a nuclear reaction or some sort of nuclear decay process. So just a review of the chapter, the magnetic flux phi is equal to the magnitude of the magnetic field times the cross-sectional area times cosine of theta. Faraday's law of induction is that the electromagnetic force is equal to the negative of the number of turns times the change in magnetic flux over time. Lenz's law is an induced EMF tends to oppose the change that is induced. So when we have an inducted current and a coil, there's a little bit of a pushback. It's almost like a resistance, and that could be calculated on an AC generator as E is equal to E naught sine of omega t, where omega is the angular frequency. And then a transformer uses induction to reduce or increase current in a secondary coil. And an electromagnetic wave consists of time varying electric and magnetic waves perpendicular to one another and to the direction of the propagation, and traveling with the speed of light, which is around 3.00 times 10 to the 8th meters per second in a vacuum.